Recording in progress.
Hi, good morning. Now I have a different issue. This is all a new experience for you, right? Usually you don't hear any sound, you don't hear any music. This time my video switcher is not on the network and I can't change the inputs. It's not one thing, it's another. So what usually happens, well, what I can try is I can try disconnecting the network and reconnecting it, but sometimes that doesn't work and I have to reboot the whole switcher. And so what'll happen is the video disappears for a moment. See, I have so much equipment now. Now everything is like a single point of failure. Here, I can at least do this, right? No, that's what we want. That one, nope. This one, nope. This one. There we go. That's me, at least. Let me just get things going. The video's going to disappear for a moment. Bloop. All right, I think it should be better now. Let's see now, which camera am I on? This one? No, not this one. This one. This one. There we go. All better. Now, because I reached behind my desk, I now have to raise my desk back up. If you don't know, the desk that I work on is my usual just work desk, but it's one of those desks that can go up and down. So when I'm doing the live stream, I raise it up to standing height. I'm actually standing right now. And then that way the camera is right in front of me. And then when I'm done, I lower the desk back down for sitting. And then that way I don't have a camera and all these monitors staring at me all day. Well, now I should say good morning. How are you all doing today?
Good morning. Doing well.
Good to
Good morning.
hear.
Good morning.
Good morning.
Mm-hmm.
You know, I'm a little disappointed. Last week I was saying, well, it's going to rain this week, because I think early last week I looked on my weather forecast app and it said indeed there was supposed to be rain this week, and then I looked on Friday and there was none. And none for the next 2 weeks. So I'm really worried that all that rain we had in December was it. That's it. That's all we're going to get.
We'll see. February is not over yet.
February's not over, that's true, but the chances start diminishing quickly once we get out of January.
I mean, I haven't even skied this year yet, so I'm really hoping for another chance.
Yeah. And my kids are all bugging me, let's go to the snow, and I'm like, well, it's disappearing, I think. Rest of you, having a good morning? For those of you who are watching on Zoom, because this is a new experience of actually having the audio up and running, you may not know that I actually usually start the Zoom session around 9 o'clock, half an hour early. And you can watch the slideshow, but also there's music playing. So I've had people come in as early as 9 o'clock and just sit there and listen.
What's the slideshow?
Oh, it's the one that you see right before my camera turns on. Just shows you what the date is and what topics we're talking about. That's the only slideshow it is. I don't know. I'm thinking if I ever up my game, I might do something like put on videos or something. Goofy cat videos from the internet. How did your first programs go over the weekend? Did you run into any problems that you had difficulty overcoming?
It was alright.
They went okay?
For the most part, I still have a few more things to finish.
Okay. But it's overall going smoothly.
Not bad, yeah.
Okay. Well, when we left off last time, we had written this program. It's a very simple program that just prompts the user to type in two numbers, and then it figures out which was the larger one and then prints that number out. Let's go ahead and compile it and run it. Enter two numbers. Let's do 3 and 5. It says larger one is 5. Let's switch them around. Let's do 5 and 3. When you're testing your program, it's a good idea to make sure you test all kind of combinations of inputs just to make sure that it's working correctly. So when you're doing a program like this, it's very tempting to always put the smaller number first and the bigger number second, just because it's kind of a numeric order. But the computer doesn't care, so make sure you switch them around. Mary asks, sometime today can we talk about pass by value versus pass by reference if that's possible? I don't think that's I don't think we're ready for that yet. We will learn about functions and passing values into functions, but I don't think we're ready yet for talking about the subtleties and how you pass those values in.
Okay. The quiz 5 or something on chapter 5, that had a question about it. So
then the information would have come then from the reading.
The book.
Yeah.
Okay.
Okay, so you probably noticed in this program that we wrote, we prompted the two numbers, and then we compare the numbers here, and then we check to see which one is larger, and we print it out. But the only difference between this print statement and this print statement is just simply what variable we print out. So whenever I see something like that, where I've got two lines that are almost duplicated, I want to feel like I want to pull that line out and just print that once. And instead of printing either A or B, I print out the value of, the larger variable. So I figure out which one is larger, store that away, and then print that one out. In other words, I do something like this. Like, let's move this printf down below the if else, because we're going to print out something one way or the other. And then let's just print out which one is the larger of the two. And then inside each one of these ifs and elses, let's assign that variable. So in here I could say something like int larger equals A, and down here int larger equals B. So if A is greater than B, I'll assign larger to A, otherwise I'll assign larger to B. Let me flip that around. If A is greater than B, I'll assign larger to be the value of A. If B is the larger one, then I'll assign the value of larger to be the value of B, and then I'll just print out the value of larger. So let me go ahead and save this, and then we'll compile it again. And we've got an error. Error, use of undeclared identifier larger, right here. So it's pointing to this right here. Now, I've intentionally put this bug in here, but can you tell me what's going on?
It might never actually get to that point. It might never execute the if-else statement.
That's true. However, it's always going to do either this one or this one. You're guaranteed to do one or the other.
Okay, yeah, true. Yeah.
It's because you're declaring the larger variable inside the scope of the if-else block.
Got it.
You move out before the block.
So in both cases here, I'm creating this variable called larger inside of this block. These two braces basically define a little box in which variables declared inside that box are local just to that box. So this variable called larger exists only inside of the body of the if, and this variable called larger, which is actually a different variable, exists only inside of this one. So when it comes down to line 17, it says there's no variable here called larger because we are now outside of those boxes. So we can say the scope of this variable larger is limited to this block of code, and the scope of this variable larger is limited to this block of code. But there is no variable called larger in the outer box. So how do we solve this problem? Well, what we need to do is declare that variable in the enclosing box. So let me go ahead and do that. I'll just go int larger right here. And good. we have compiled the program, and now we'll run it. I entered 3 and 5, and it says the larger value is like negative some really large number. Let me try running it again. I get a different number. So we get apparently a different random number each time I run this program.
But you're redeclaring or larger. It's basically two different variables, right?
Yes. So in the outer block, I've got a variable called larger. And in this inner block, I have another variable called larger, and this is a different variable. It's got the same name, but it kind of overlays the existing outer one so that it now becomes the variable inside that inner scope. Once I leave this inner block, this variable goes away, and the other one returns. However, since I never assigned to this value, it gets whatever junky value is in there to begin with. And so that's what appears down here. So how do I solve this problem?
Remove the type
From where?
from the inside the if statements.
So when you put a type out in front of a variable name, you are telling the compiler, I want to create a new variable. That's how it actually knows the difference between using a variable and declaring a variable. When you declare a variable, you put the variable name and its type out in front, and that says, make a new variable of this name with this type. When you remove that type information, then you're just using an existing variable that's already been declared. So I hope this should be able to fix the problem. Seems to have worked. Very good. Okay, there was a question here. What's the advantage of using clang over CMake and make? Well, so clang is the compiler itself, and CMake or make is just a tool to automate the compilation for you. CMake and make are not themselves compilers. They're just a tool to run the compiler automatically. So I'm just using the compiler directly here. And later on in the course, we'll learn how to use tools like make or CMake to help build the programs for you. But right now, we're just using the low-level tools, and then we'll start layering other tools on top of that. Okay, so that fixes up that problem, and I kind of like this better because we are only printing out that line once, and then inside of that if and else we're just assigning to a variable. So that way if I have to change what gets printed out, I only have to change it in one place. Any other questions about that? Okay, so let's do a different problem. So let's say I am a television installer. My job is to come into your home and look at your setup and tell you what size of television you should buy in order to fit into your home decor. So you've decided as a homeowner that what you want to do is you want to buy a television that fits very nicely above your fireplace. So your fireplace is a certain width. And you want to buy a television that is exactly that same width. Now, as you know, if you go into a store and you want to buy a television, it is not, when you buy the television by its dimensions, you're not buying it by its width or its height, you're buying it by its diagonal measurement. So when you go to the store and you buy, let's say, a 36-inch TV, which is small by today's standards, you're buying a TV that is 36 inches diagonally across, not horizontally, not vertically. So what we want to do as a television installer or recommender is write a program so that we can input the width of the space that we want to put the television, and it tells us what size television to buy. So that's what we're going to do over the next couple minutes, is solve this problem. So any ideas how we could calculate that? We're given the width of the fireplace, and it calculates the diagonal size of the television.
Pythagorean.
Pythagorean Theorem. So the Pythagorean Theorem says that if you have a right triangle of a certain height and width, we can calculate the diagonal length. So we have width squared plus height squared is equal to the diagonal squared, or we can rewrite that and solve for D as the square root of the width squared plus the height squared. Okay, so we could plug in the value of the width right here, but in order to be able to calculate the diagonal, we also need the height.
Well, we have aspect ratio, right? So we can use the standard aspect ratio to find the height.
Yep. So TVs these days come in a standard what's called aspect ratio, which means the ratio between the width and the height of the television is always a fixed amount. And it's slow, I guess it's slowly changing. Sometimes you can get now like ultra-wide televisions, but for the most part, they come in a standard aspect ratio. And that aspect ratio is, do you know what it is?
16:9.
Yeah. So if you had a television that was 16 inches across, it would be 9 inches tall. So how can we use this information to help us solve this equation?
Is a ratio.
So we can use set up a ratio, and we'll do 9 over 16 equals h over w. So whatever ratio h and w should be in, it should be the same as this ratio, 9 by 16. Which means now if we do the cross multiply thing, we'll get 9w equals 16h. And since we are trying to solve for h, we'll get h is equal to 9w divided by 16. Great. So that means that we could have the user input the width of the television, we'll calculate the height of the television, and then plug those two numbers in to our distance formula, Pythagorean Theorem formula, and be able to calculate the diagonal width, and then tell the user they need to go out and buy a television of that size. So let's go ahead and do that. Let's write this up. We'll start by asking the user how wide the television needs to be. And let me make a variable for that. And now let's calculate the height. So int height is equal to 9 divided by 16 times the TV width. I'm not satisfied with the name of this variable. I'm just going to change it to width. I mean, that's where we're talking about the TV everywhere here. I was thinking I wanted to distinguish between the fireplace width and the TV width, but we don't really care about the width of the fireplace. All we care is about the width of the TV. So I'm just going to make this width. Okay, so we've got the height now. And the next thing would be to plug that into the Pythagorean Theorem formula. So let's go int diagonal is equal to, and I'm just looking on our notes over here. So I'm going to take the width squared and the height squared and then square root the whole thing. Easy way to square the width is just multiply it by itself. Oh, the question is there a reason why I'm not passing in width here by reference? And that's because I'm a professionally trained idiot and forgot to put the ampersand on there. The compiler would have caught that. All right, width times width plus height times height. And then there's a function called sqrt for calculating the square root of a value. And then now we can print out the number we're looking for. And since this, this unfortunately is this is an American podcast, or not, why am I saying podcast? It's an American stream, so I can do this all in inches. Even though it would probably be different dimensions in different parts of the world, but we'll go with inches. All right, so that's our program. Very quickly, we ask the user for the width of the TV. Use Scanf to get the width, and then we calculate the height using the aspect ratio. Then we plug that into the Pythagorean Theorem formula. We square the width, add it to the square of the height, take the square root of the whole thing, and then compute the diagonal. And then finally we print out the answer. So let's go ahead and save this and compile it. Oh, got a bunch of errors. Let's go back and look at these errors. So first one says, implicitly declaring library function sqrt with type double, here it is, must include the header math.h. Oh, okay, so the answer to this is we have to include math.h in the top of the program up here. So let's just go ahead and do its recommendation. And this is here because by default, your program doesn't know about all these math functions. There are math functions like square root, tangent, sine, cosine, exponent, logarithms. Those are all not included in your program by default because most programs don't need these trigonometric and more complex math operations. Most programs just need the basic multiply, divide, add, subtract. So these are extra. You have to bring them in separately. Okay, and now we've got a different error. This one looks probably completely different than what you have seen before. Most of the time you get an error that looks kind of like this up here. You've got something in purple, you've got this green arrow probably pointing to where the error is, and this one here looks completely different. Now there's some stuff that's hard to read up at the front, but the error message is back here. It says, in function main, there's an undefined reference to square root. Linker command failed. So this is a different kind of error we've seen before, and this is caused by the compiler not knowing how to actually do the square root function. It knows that it can call the square root function, but it doesn't know how to actually do the square root function. And so to solve this problem, we have to add an extra flag onto the compiler to tell it how to do the square root function. So that is done by typing -L and then M. And that means to link in the math library. And the math library, since it's fairly common to link in the math library, it's just called M for math. And now it has successfully compiled, and we can run it. So width of TV, I don't know, give me a width of a television. Let's go with 40. And it says, oh, well, that seems strange. We calculated the width of the TV, or we inputted the width of the TV to 40 inches, and so the diagonal ought to be longer than 40, but it came out to be 40. So we've clearly got a bug in this program. Let's go and look at it. Faced with this issue, how could we start debugging this problem? If you know what the error is, you can probably jump right in and fix it. But if you don't know what the error is, if you don't know why it's causing this, the program is running, so there isn't a syntax error. There's not a problem with the actual construction of the program. There's a logical error in the program. Something is not being calculated correctly. How would we go about trying to find where this problem is?
I mean, if you don't know exactly what the error is, you can start outputting, I guess, them one by one.
Yeah, this is called debugging by Printf, or debugging by print statements. You just sprinkle print statements through your program, hoping and looking at the output of each one of those and comparing them against what you expect the value to be. So let's print out the value of height. And then, of course, down here, we're printing out the value of the diagonal, so we're going to get that. So this is just the new print statement we're going to put in there and see if this comes out to be what we expect. So I could actually start by putting in something like the width be 16, and it should display 9 as the height. Or I could put in 32, and it would display 18 as the height. Let's put in 32. I would expect it to say the height would be, what did I say? Not 16, 18. I would expect it to say the height is 18 if I put in a width of 32. And it comes up with 0. So that kind of tells us that something's wrong with this calculation. Let's go back to our calculation over here. Let's just make sure that our formula is correct. We've got height is equal to 9 over 16. Now, I've written it here as 9 times W and then divided by 16, whereas in my program I wrote it as 9 over 16 and then times W. I wonder if that makes a difference. So let's try that. I mean, mathematically it shouldn't make a difference. Oh, well, that seemed to fix it. So why did that work, but the way I had it before did not work? So just to review, what I had before was 9 over 16 and then times the width. So like I said, algebraically, those are the equal to each other. All I'm doing is just moving the W out here. But programmatically, apparently, they are different. So, does anyone know why one seems to give the correct result and the other one doesn't?
Because 9 divided by 16 in the program equals 0.
Good. Because 9 and 16 are both integers, when the program does the division, it just does it as integer division. So 9 divided by 16 as just integers is 0. And so we get 0 times the width, which is our calculated height. So what changed when we moved the divide by 16 out to the back? So
Well, now you have a whole number that's bigger than 0 because 9 times the width is bigger than 16.
Good. So we take 9 times the width, which was 32, and we get like a fairly large number, like 400 and something. And then we divide by 16, and now we get a number that is not 0. So when you're dealing with integer arithmetic, it can change your answer depending upon how you structure your calculation. Now, somebody on the YouTube chat said there's another solution to this. Let's go back to 9 divided by 16. And that is to force the compiler not to do this as integer division, but to do it as float or double division, so that we get an answer that is not 0. And there's a couple ways we can do this. One easy way to do it is just change the type of one of these numbers, not from an integer but to be a double or a float. Just put 9.0 and 16.0, and now it will do the division as probably a double. It'll do the division as a double. And then we'll multiply by the width. So let's see if that changes things. So that worked pretty nicely. I was able to move that division out to the front, but by forcing it to do as either floats or doubles, I now ensure that I don't just get 0 out of that fraction. So does it do it as a float or does it do it as a double? I know, like in Java, if you do division like this, it comes out as a double. Double is like the default type. Float is like a special one. I'm not sure if the answer, if it's the same way in C. What it'll do is it'll do it as whatever's the most natural floating point type for the processor you're on. So if our processor does doubles most naturally, then it will output as a double. If it does floats most naturally, then it will output as a float. Another question is, what would happen if we do 9 divided by 16? So we take off the dot zeros on there and just make this be a double instead. Now you think about that. I've changed the type of height to be double. And while you're thinking about that, what I need to do is I need to go back through the program here and change my print here to work with a double rather than an integer. So you think about, what do you think is going to happen here? What do you think it's going to output? And then we'll go ahead and run the program and see if your prediction is correct. Do you have a prediction? I think it's going to say 0. I think it's going to say 18 if I input a width of 32. I think it's going to say 18.0. How about 18 point and then a whole bunch of decimals after it? Let's see if your prediction was correct. 0. It says 0. Okay, why did it say 0 and not 18?
Because you're assigning to a double integer of 0.
Yeah, so it does this division first. Integer divided by integer is still integer. So I get 0, multiply that by the width, I still get 0, and then I assign it to a double, but I'm assigning the value 0 to it. So changing the type of the variable we're assigning to doesn't change the precision with which the actual calculation on the right-hand side of the equal sign is done. So we need to make sure the calculation on the right-hand side is done with the kind of precision we want, and then we can assign it to the variable. Now we're working, most of the time, when we're working with televisions, we're working with TVs that are of an integer width and height. When you buy it in the store, it'll give you the diagonal measurement in inches as an integer, even though the actual diagonal may be slightly more or slightly less. In fact, I've noticed when you go to the store, it'll say something like, this television is a 55-inch class television. It's a 55-inch class television. And what that tells me is the marketers, the people that make the televisions, have grouped together all the televisions that are approximately 55 inches, more or less, and said that they're just 55. So they may actually be like 54 and a half, or they may be 55 and 3/4, or they may even be low as 54 or 53, because as long as they're still in the class of televisions that are 55 inches, then they can say it's 55. Always be on the lookout for a little marketing speak like that. I'll bet you if you measured your television, it's not really what it said it was. And part of that is because maybe the panel that's inside the television was manufactured to be, let's say, a 55-inch, but because the panel has to be overlapped a little bit with the bezel around the edge, even if the bezel is really small, there still has to be a little bit of overlap so the panel stays in there. That's going to make the panel, the visual area, slightly smaller. And so they could have manufactured it to be 55 inches, but the actual viewable area is 54 and a half because of that overlap. But they can say it's a 55-inch television because that's what's inside. Okay, so let's put this calculation back with the dot zeros on there and see if that changes the output. Okay, width of TV is 32, so height is 18, and we have to buy a TV that is 36 inches. And let's go a little bit bigger. Let's say we have a fireplace that is 48 inches wide. So the height would be 27, and we have to buy a 55-inch TV. And that'll fit nicely on top of the fireplace. Okay, there's another way to do this calculation. We use the Pythagorean Theorem to do this. We can also do this problem with trig functions like sines and cosines and tangents. Now, some of you probably have to reach back into your trig class. How can we calculate the diagonal given the width without using the distance formula? Do you remember this? So we've got our right triangle. Here's the height, here's the width, here's the diagonal, and then there's an angle here. We'll call it theta. And we got some trig identities. The sine of theta is going to be the height over the diagonal. The cosine of theta is going to be the width over the diagonal. And the tangent of theta is going to be the height over the width. So which of these formulas can we use to help find the diagonal from the width?
Cosine.
Oh, we'll use cosine, because that actually uses the two variables that we need. So we've got cosine. Oh, well, I already have it written here. So let's solve this for d. Let's solve this function for d. So I get d is equal to w over the cosine of theta. But the problem is, I don't know what this number is. I don't know what this angle is. So we need to figure that out. So again, which of these formulas will tell us what this angle is? Tangent. Tangent will work. All we need is the width and the height. But we don't know the height, right? Because that's what we need to calculate. All we know is the width. However, we do know the aspect ratio. We do know that it's a 16 by 9 triangle. So we've got tangent of theta is equal to the height over the width, which is 9 over 16. And then we solve that for theta. We've got theta is equal to the, what is this called? The arctangent?
Sure.
9 over 16. So let's go back to our program and let's modify it to use this, this other technique. So in this one here, we actually don't need to calculate the height. And we're going to calculate the diagonal a different way. So this is the Pythagorean formula. And then down here we'll do it using trigonometry. Now here we're probably going to have to work with doubles because this angle is not going to be a nice, the angle, by the way, is going to be, it's probably not going to be a nice degree amount, so we'll have to use doubles for that. So we'll double theta is equal to, I think the function for doing the arctangent is called atan. And we're going to put in 9.0 divided by 16.0 to make sure we get a we don't get 0 out of that. And then double diagonal is equal to the width, which is up here, divided by the cosine of theta. And then we'll print out the answer. And since the answer is going to be a double, we have to change this to LF to print out a long float, and I think that should do it. So width of TV, let's put in 32. That'll give us a height of 18, and it should give us, if we're using the formula correctly, it should give us a TV that is 36 inches wide. And well, it's pretty close, 36.7. That may actually be what our original program was trying to do, but because we were doing it almost entirely in integer arithmetic, we were dropping off that decimal portion. But this looks pretty good. Let's try putting in 48. That should give us 55 as the answer. We get, yep, pretty close, 55.07. So I think that's right. So we can do this the trigonometry way by using arctangent and cosine, and then we can calculate the answer that way. And this one, we don't have to calculate the height, but we do have to calculate the angle. All right, any questions on that? No, we're good? Okay. So now I want to switch gears a little bit and talk about functions. So I've got two ways of calculating this diagonal. I've got the Pythagorean way and I've got the trig way. It's basically two different ways of calculating the same thing. And if I want to do it one way, I have to comment out the other way. And then if I want to do it the first way, I have to comment out the second way and make it do it the first way. I think it would be better if we took these two ways of calculating the diagonal of the TV and put them into functions. So a little bit about functions. In C, first of all, they're called functions. In Java, they're called methods, but they're basically the same thing. A function is a block of code with a name. It may or may not take some parameters, also called arguments. And then it may or may not return a value. So a function always has a name. It may have some parameters, and it may return a value. If it doesn't return a value, it's declared to be void. That just means the function does a calculation. It maybe prints something on the screen, but it doesn't return anything back to the program. And then every function also has a body where it actually takes the values coming in as the inputs or parameters and then does a calculation on them and then potentially returns that value back to the program. So that's what we're going to do here. We're going to make two functions, one that calculates the diagonal using the Pythagorean way and one that calculates it using the trig way. So let's make a function called let's call it trig diag. We're going to pass in the width. Let's just call it W.
You're not sharing.
Oh, sorry. So I'm going to make a function called trig diagonal that pulls in the width as a double and then returns a double. And then I'm just going to basically take these lines that I had written up here, and then we're going to return the diagonal. And now I just need to fix some things here. Let's see, this should be W for this one here, theta, and then diagonal. That looks good. I'm just going to call this D. And now I can take this out and go double diag equals trig diag, pass in the width, and then let me do the same thing for the Pythagorean way. So I'm going to take these lines out. I'll make this one a double as well. Pythag diag. I don't need to print out anything. And we'll go double D, and then this will be W, W, H, and H, and then finally just return D. Okay, and then over here I can say double diag equals Pythag diag, width, and then to enable one or the other, I just comment out the one I don't want. So let's do this with the Pythagorean way first. Comment out the call to the trigonometric function, and then let's compile it. And we got an error. So there's nothing syntactically wrong with my program. Like, I've got all the pieces in there. If I was to take this program and compile it as a Java program, it would work. But it doesn't work in the C compiler. And that is because the C compiler is what's called a one-pass compiler. The C compiler takes one pass through your program, and it compiles as it goes. So it's going to start here with main, and then it declares a variable called width, calls printf, calls scanf, and then here we've got a call to Pythagdiag. But the compiler complains because it doesn't know about this function yet. It's making one pass through your program, so it doesn't know about the existence of a function called Pythagdiag. Now you might be asking, how does it know about printf and scanf? Well, it gets those from this first line up here, standardIO.h. Includes the declarations for those functions. So by the time it gets to lines 8 and 9, it knows about printf and scanf. But it doesn't know about our function called Pythagdiag because it appears below main in our program. We can solve this problem by moving the function definitions up above main so that they're known to the compiler by the time it gets around to calling those functions. Let's go ahead and do that. I'm going to take these two out, and we're going to put them up above main. Now let me save it and compile it, and now it compiles just fine. So that is a very important difference between a C compiler and a Java compiler. In a Java compiler, you can kind of put all the methods in whatever order you want. In C, they have to be structured so that they are defined before they are used. So before I use the function in main, I have to make sure that the function definition is known to the compiler. And that puts kind of a restriction on how you structure your programs. It means that functions that use other functions have to go down at the bottom, and the functions that don't depend on other functions need to go up at the top. And that is often exactly the opposite of the way you actually want to structure the program. Usually, I want to put the main at the top so that people can find where the entry point of my program is quickly, rather than having to scan through or scroll all the way to the bottom. And I want to be able to put the small functions, the auxiliary helper functions, down at the bottom because those aren't as important as main is. So I want to be able to structure it so that main is at the top and those smaller functions are at the bottom. But I'm limited by the fact that the C compiler needs to see it the other way around. So there is a technique you can use to solve this problem. And that is, let me go ahead and move these to the bottom where I think they ought to be. So now they're down at the bottom again. Take just the header line, just the function declaration of each function and paste them up before main.
We're not seeing your screen.
Sorry, I keep forgetting to switch it. So I moved those two functions down to the bottom, and now I am copying and pasting the declaration lines of each function and putting them up above main. And then just put a semicolon on the end of each one of these. These are called function prototypes. They exist just to let the compiler know about the existence of these functions. What you're telling the compiler is, there is going to be a function called trigdiag that takes in a double and returns a double. I'll tell you about the name right now, and I'll give you the body, the actual code itself, later on. But this contains enough information so that when I call the function, I'm speaking for as the role of the compiler, I now know enough information about that function to be able to call it and to be able to use its return value. So I can now structure the program the way I want to structure it. Main goes at the top. There has to be a few function prototypes right in front of main, but that's a fairly small body of code. And then the actual functions themselves can go down to the bottom. So by using function prototypes, you essentially allow yourself to structure your program in any way that you want. The function prototypes have to go first, but then after that you can define your functions in whatever order you want. So I have to be careful about words that I use. Down here at the bottom, these are function definitions. They define what the function does. They contain the body of the function. Up here at the top, these function prototypes, those are function declarations. They just declare the name of the function and the parameters they take, but they don't contain any code. So the real answer is functions need to be, here we go, functions need to be declared before they are used. They don't necessarily have to be defined. They just have to be declared. Function prototypes allow you to use a function before it is defined. It still has to be declared, but you can use it before it's defined. Okay, so let's go and switch out the call to Pythagdiag with the one for the trig function, and we'll compile the program. You can see it compiles just fine with no errors. And we can put in...
Yeah, about that. We can't really see.
Oh, I keep forgetting to switch the input. The problem is that the screen that shows what input I'm on is like over here, and I'm looking down here at my laptop, and it's out of my field of view. I need to put another little like monitor right in front of my, right on top of my my laptop that shows me what you can currently see. And then maybe if visually I can see those are different, then I have to remember to switch it. Or what I need is like a motion sensor, right? So if it sees something motioning over on my iPad, switch over to that. If it sees something motioning on the screen, switch to that. Or I just need to get better at switching. Anyway, so I ran the program. I inputted 48, and I got the same answer as I did for the trig version. Okay, any questions on that? So function prototypes are really easy. You just take the declaration section of the function and you copy that up above main or wherever you're going to be using that function. Typically they're up at the top of the program, and you just put a semicolon on the end. That's all you got to do. The downside of function prototypes, this is the downside of the C compiler, is it means that anytime you change something like the name of the function or the parameters it takes, or its return type, you also have to change the prototype. So there's two different places to change it. That, I think, was one of the things that the people who made Java were looking at, which was they wanted to make sure that you could do it in any order you wanted. And so very easy, you just make it a two-pass compiler. One pass to learn the names of everything, and then the second pass to actually do the compilation. But that means that now you only have to maintain the names of functions and the parameters, or in Java's case, the names of methods and the parameters in one place, not two. Okay, so now that we got that done, there's probably some questions that are lingering, which is, what's going on with this -lm thing here? What does that do? And also, like, why did we have to include this math.h? And why did we have to do both? Why did we have to put this in, this include line, and do this lm? Neither one of them alone was able to solve the problem of using square root and sine and cosine and tangent. Why did we have to do both? And to answer that question, we need to talk briefly about when I type in the clang command here, what's actually going on? It's not just one thing. There's actually many things going on behind the scenes. And so let me give you a little introduction to that. So when you compile a program, it actually goes through several phases or stages that progressively takes your program and transforms it ultimately into the assembly language and binary code that the processor can execute. So you start with your C code, and then it goes through these transformations to turn it into the ones and zeros the processor can actually execute. So when you start out, you've got your .c source code, and then that goes into the first stage, which is called the preprocessor. And then what comes out of the preprocessor is your C code, but without those hashtag directives. So all that stuff has been stripped out. And also, comments have been removed. So any comments you had in your program, those have been stripped out as well. So what happens to those things? Well, so the preprocessor takes those include directives, and it goes out to the compiler's file structure. So there's a whole bunch of files that came with the C compiler, and one of those files is called stdio.h. When it finds that file, it takes the contents of that file and actually just copies and pastes the contents of that file right into your program. So where that include standard IO line was is now going to be the contents of that file. And their standard IO.h file is fairly long. It's like 1,000 or so lines long. And so your program is now going to grow essentially by 1,000 lines. So when you type in include and then a file name, it actually takes the contents of that file that you're including and drops it right into your program. Same thing is happening with that math.h file. It goes and finds that file, takes the contents of that file, and drops it right into your program. So what's in those files? Those .h files contain just function prototypes. They don't contain any actual code, just function prototypes, and also things like constants and globals, but no actual code. So what's the purpose of that? The purpose of that is to make sure that your program knows about the declarations of all those functions before you use them. If I take out these includes, let me take out this one, save it and compile it, then we got a whole bunch of these errors that says, you're trying to call this function called printf, but I don't know what it is. And you're trying to call scanf, but I don't know what it is. So the reason we put that up there is to declare the functions printf and scanf so that the compiler knows about them, and later on we're going to get the actual code for how those functions do their jobs. And according to the comments, yes, there's other things that the preprocessor does. We'll get into that later, but right now all we know about that are the includes. And so those includes just simply get removed and replaced with the contents of those files. And yes, there's things called defines, and there's ifs and elses you can put in there, but that's not a topic for today. Okay, so phase one, take your C code and replace those includes with the contents of the files that you're actually including, and those bring in all the function prototypes that your program needs. So next phase, you start with your pre-processed C code, and then it goes into now what we would actually call the compiler. The compiler's job is to take your C code and turn it into assembly code. Assembly code contains the fundamental processor operations like load and store, add, subtract, multiply, compare, branch. Pretty much, well, not pretty much, every single program, no matter how complicated, can be broken down into these just a few dozen or so basic fundamental instructions that the processor can execute. That's what the compiler does. So the preprocessor doesn't really do any compiling. It just simply removes the includes and replaces them with these files that contain function prototypes. And then the real compiler takes over, and a compiler's job is to translate a program in one language into a program in another language. In this case, it's going to be assembly code. Next phase, we're going to take our assembly and put that through the assembler. Which is in itself another compiler. It's taking the assembly code, and now it's going to translate that into the binary or executable code that the processor itself understands. So assembly code is a human-readable programming language, but it's the programming language of the processor. And then the assembler's job is to take that human-readable code and turn that into the human-unreadable ones and zeros that the processor actually understands. Now, this binary code is not a complete working program yet. This binary code is also called object code because it has been targeted. Its object is the processor itself that you're going to run the program on, but it's not a complete working program. It is just simply the contents of your C code translated into the ones and zeros. So this is also called object code. It has nothing to do with objects, like in a Java sense. And then finally, the last phase is called the linker. So the linker takes your object code and it attaches on pre-compiled what are called libraries that contain the code that your program needs to actually be a fully functional program. So by default, it also brings in, the linker also brings in the C standard library. This contains the actual functions for things like Printf, Scanf, the file input and output, networking code, auxiliary functions for doing things like searching, sorting. So there's just like hundreds of functions that most programs need to be a fully functional C program that can run on our operating system. So the linker's job is to take your code, the binary, the object code, and link in these other libraries to make a fully fleshed out executable. Now in our case, our TV program, we also need to bring in the math functions. And so the linker's job is to bring that in as well. So in our compile command, when we say -lm here, we're telling it, link in the math library. The math library is just called M. The C library, by the way, is just called C, but you get that one by default. You don't have to explicitly say, I want to link in with the C library. You always get that one. And then when the linker has done its job, you now get a executable. Okay? So when you type in that clang command, that's really just what's called a front-end script or a front-end program whose job it is to spawn off or launch these 4 other things. Launch the preprocessor, then launch the real C compiler, whose name is not clang, it's something else, and then launch the assembler, and then finally launch the linker, and then piece together your entire working program. You can actually stop this process at each one of the phases and see what it outputs. All you have to do is pass in the appropriate flag to the clang command, and it will run all the stages of the compiler and stop when you tell it to. So if you want to see the output of the preprocessor, you just pass in the -E, capital E flag, and it'll stop after doing the preprocessor. If you want to see the assembly code, you pass in capital S. And if you want to see the object code, you pass in little c. Let's go ahead and do that. Actually, what I'm going to do is I'm going to go back to hello.c because it's a nice short program. So let's go clang-e hello.c. So nice short hello program. And I'm now going to run this program, or run this compiler. Okay, so here's my program at the bottom. And then up here above it are all the function prototypes for anything related to input and output. So there's stuff in here that has to do with file input and output. And if we scroll up enough, we should eventually see the function prototypes for Printf and Scanf. Let me just keep scrolling. I think we're getting close to it. Did I miss it? Nope. We'll just keep going. It's there eventually. Like I said, this standard io.h is, there it is, Scanf. And this is how a Scanf is actually defined. All right, it looks complicated, but that's the way it actually works. And then if we scroll up a bit further, oh, here's Scanf again. There's actually 2 versions of Scanf. There's this one, and there's this one. This one looks a little bit similar. Looks a bit simpler. And then if we go up a little bit further, we should find Printf. Here it is. There's Printf. Notice that these are all just function prototypes. It's just a declaration of the function, and then the argument list, and then a semicolon. And by the way, this ... here allows you to declare a function that takes an unknown number of parameters. You have to pass in at least one, which is your format string, and then everything else after that is optional. So that's what the ... allows you to do. Okay, and so we come over to our TV program. Let's go ahead and compile that. We can see that our program is at the bottom, and then above it are all the function prototypes plus things like constants for all the math functions. So the Clang compiler, in doing the preprocessor phase, literally took the contents of the math.h file and the standard io.h file and just dropped them right into our program, as though that's what we had typed all this time. You know what we could do? We could actually take the contents of these files and just drop them right into our program right here. And the compiler would be none the wiser. That's what had happened. In fact, we don't even have to put the entire math.h there. We could just put in just the function prototypes for, what is it, a tangent and cosine. Let's go ahead and do that. Double cosine, double t, and double atan, double t, t for theta. And then let's take out math.h. Oh, we also have to put in square root, double square root, double x. And I think that's it. So I took out math.h, and I just put in the function prototypes for cosine, arctangent, and square root. And let's see if our program compiles. It does. It worked. Got the same answer. So, do I have to put in the includes to make my program work? Absolutely not. All those files contain is just function prototypes. And so if you can obtain those function prototypes, you can just paste those into your program and it'll compile fine. It's easier though to just include that file. Okay, let's take a look at the assembly code. Remember, we can get the assembly code by passing in the dash capital S. Clang tv.c dash capital S. And we've got a new file over here, tv.s. Let's go look at it. This is the assembly language code for our program. You can probably see in here, there's things like multiplies, adds. Here's a call to square root. What else we got in here? Move, divide, a call to cosine, a call to atan. So these are all the fundamental operations of the processor. And this is our assembly code. And finally, we can do clang tv.c dash little c, and we end up with another file, tv.o right here. That's our object file. And we can't look at that. It's just, you know, for the most part, gibberish. I mean, there's a few things in English in there. Things like our strings. So our prompts are going to appear somewhere in here. But for the most part, we can't really just look at this because this is actual compiled code. Okay, so you can stop those stages of compilation at any point, and you can inspect what it's doing. Any questions about that?
So I have a question.
Yeah.
I don't know how to explain it, but like, so when you write the headers for the functions on top, like the math functions, why, how does the compiler know like what's in like the body of the function if you're pulling it from the, I'm sorry, I'm like trying to figure out how to say it, but like the body of the function for like square root, you put it on top, right? And how does the computer know or the compiler know like what to do with that function if you just put the header, if you don't define it?
That's a great question. So the question was, if I just put in the function prototypes up here and it compiled just fine, how does the computer know to actually like, how does it actually know how to do the cosine and the sine and the tangent functions? Let me see if I can answer that quickly here. So again, the .h files contain only function prototypes. So when I swapped in my function prototypes, I wasn't doing anything different than the math.h file does. All that's in there are just the same kind of things that I just wrote, except there's more of them. So actually, if you look at the assembly code that gets outputted, you'll see that in my program there is a call to square root.
You gotta share your screen, sorry.
Oh, sorry. So inside of my program, inside the assembly code, there's a call to the function called square root. But nowhere in here, if you scan up and down, you can see here's the definition for trig diag, and here's the definition for main. But there's a call to square root, but there's no actual code for square root anywhere in here. In fact, if I did a search, if I said find square root, and what I'm looking for is something over on the left-hand side that tells me that this block of code, this block of assembly language instruction, belongs to the function called square root. I have a call to square root, and then just a declaration of the name square root, but no actual code for it. So this is one of the things that the linker does. My object code here contains a call to square root, but not the actual code for it. The actual code for it is contained here in this math library. Someone has actually written the code for doing square root, and then compiled it, and then set it aside, actually in its own object file. So my object code, the C standard library, which is also an object file, and the math library, which is also an object file, contains the compiled versions of each one of those functions. And one of the jobs of the linker is to resolve all of those issues. So it sees that in my program, there's a call to square root. And it sees in the math library, there's the actual code for square root. And then it makes that connection.
I understand that. Thank you.
All right, so the linker says, oh, there's a call to square root, and over here is the code to square root. I'm now going to link those two things together. So when I call square root, it actually invokes these set of instructions. And when I call printf, it's going to invoke this set of instructions that are over here in the C standard library.
That makes a lot of sense.
Good.
Yeah, thanks.
So that actually gives me a good idea, maybe for next time on Thursday. We are going to take these functions, these diagonal calculating functions, and we're going to essentially do what the standard library and the math library does. We're going to move them into a separate file and then compile those separately from our program and then link them together.
Okay.
Cool?
Yeah.
All right?
Yeah.
I mean, that's kind of like really what I want to do with a course like this. It's like I can show you the C syntax, I can show you how to compile the programs, but you have these questions like, what's going on under the hood? How does this actually work? And this is the stuff I really like to talk about because it's not in the book, really, but it gives you a lot of insight into like what's going on. And the same thing happens in the Java programs that you write. If you write a class that calls the methods for putting something on the screen, like a J-frame and buttons and scroll bars, well, your program doesn't contain any of that code. But when you run your program, it links all that stuff together, and then when you invoke the method for putting a J-frame on the screen, it actually knows to run the code that's over here in this other file. Anything else? Oh, I love this stuff. I love being able to talk about this stuff because it's just so cool how it all clicks together. Like it clicks in the sense that like it's when it all works, it's really smooth, right? You just compile your program, and then all this stuff happens behind the scenes, and all this stuff gets assembled and put together, and then boom, you got a working program. But all this stuff had to happen ahead of time. Someone had to design and build all of this stuff so that when you compile your program, it just comes together like that. But I'm laying the foundations now for being able to talk later on in the semester about how can we compile and link together larger multi-file programs where you've got 3 or 4 or 5 different files that contain parts of your program, and you need to put it all together and make a working program out of that.
Yeah, that's what I did in Java because I took CS or CSCI 13, so more second Java, so that we were doing that. So I was like wondering, oh, can we do that with C? So
absolutely.
Basically answer the question.
In C, the linking stage happens up front when you do the compiling, and in Java, the linking stage happens later on. So you invoke the compiler. When you click on that little compile button on your IDE, whether it's JGraphs with a little running guy or Eclipse or IntelliJ, usually there's a button to click on that says compile, but all it does is it just compiles all of the programs all of the files that you can see. When you actually run the program, then it links all the stuff together very quickly, and then you get a working program. In C, it's kind of reversed. You compile, you link together, and then you get your working executable, and now, for the most part, that executable can kind of stand alone, and no additional work has to be done. I'll put a caveat on there to say that the linking is actually done in 2 stages. There's compile time linking and then runtime linking. So I'm lying to you a little bit and saying it's all done up front, but you can actually pass in flags to the compiler to tell it do all the linking up front and give me a standalone executable that doesn't need any of the auxiliary stuff at all. You'll find the program is much bigger because all that stuff gets linked in together. So instead of your program executable being just a few kilobytes, it might be a few megabytes because now it contains everything you need. We'll get into that later.
You're saying for the linking done up front, right? The bigger executable. Okay, so with the smaller executable, you have to include the libraries, right? For the runtime compiling, runtime linking, right?
So what happens there? Like I said, I was going to do this later. So what happens
sorry.
there is compile time linking just simply resolves things like okay, I know there's a call to square root, and I know the body of the square root function is over here. And then when you run the program, there's a runtime linker that actually now joins those two things together and resolves the addresses. So there's a call to square root, and then let's say the square root function itself is residing at memory location 5000. And so what it does is it goes back into your program and says, okay, the call to square root, I'm going to replace that with a call to 5000. And then it actually calls the code. So very quickly, it just runs through your program, finds all the places where there's a call and replaces them with the actual addresses of that code, rather than just placeholders. And the benefit to there is I can now have one math library that all the programs that need it share, rather than having every program have its own copy of the math library, which would just like use enormous amounts of disk space. Same thing for standard I/O. All my programs that are running can share the same standard C library, rather than every program having their own copy of it.
I see.
It also has the benefit that if I find a bug in the standard C library, I can replace the standard C library with the fixed version, and now all the programs suddenly get to use the new version.
Okay.
Yeah. Good. Great question.
Sorry, and this happens every time, right?
Yes.
For during link time.
Yep. So every time you run a program, this all happens behind the scenes.
Okay.
So actually in the compiler it's called the linker, and the runtime linker is called the loader. There's the linker and the loader.
Thank you.
You're welcome. Any others? Oh, this was a great class today.
Yeah, I agree.
Yeah. it's just going to get better, right? But all this stuff about stages of compilation, right? That's not in the book, right? But it's good stuff to know. Okay, well, we've reached the end of today. It's 11 o'clock. And so we'll pick up where we left off next time on Thursday. We're talking more about function prototypes and how can we move functions into their own files and then link them together. And then we'll start talking about the assignments for this coming week. All right. Well, I don't have any more for you today. So I hope you have a great day. And I will see you on Thursday. And some of you I'll see tomorrow in my other class.
That was great. Thank you.
You're welcome.
Thanks, Professor. See you.
Yeah. Take care, everyone. Oh, my son says hi. He's sick today, so he's home from school. All right, take care. Bye-bye. Hold on here. So are there any good books on C? Let me look through the chat here. Let's see.
Why are you looking to the chat?
Oh, I'm still streaming on YouTube right now. Good books on C. So we are using, in this class, we're using a book called C for Programmers. So it assumes that you already have at least one programming language that you know, like Java or Python, and then it just picks up where that left off.
Hello, streaming friends.
Hello. So we're using one called C for Programmers. Let me see if I can bring that up on the screen here. Hey, please. So that's this one here. C for Programmers with an introduction to C11. And then there's other books here that I've actually not looked at. Computer Programming for Absolute Beginners. What else? You know, you can always go back to basics. There is the C Programming Language book. Here, the C Programming Language book. Now, this is a very old book, 1988, so pretty old. And it's actually not up to date with the latest C standards, but a lot of people say this is kind of the quintessential reference for the C programming language. And it's very short and concise. It's a fairly small book, maybe no more than about this thick, like less than an inch thick. So very, very concise reference manual for the C programming language itself. Again, if you already know another language, this is a pretty good one to go with. But it's not completely up to date with the very latest C standards. So those are the books we use. Oh, and there's one other book. Actually, when I was scrolling through here, I saw a book that looked interesting. Wish I should look at this one here called Little Book of Pointers. There's another book that I recommend for the course called, oh, now I forgot the name of it. Let's put in C pointers. Ah, here we go. Understanding and Using C Pointers, an O'Reilly book. So that has a really great couple of chapters on introducing pointers and how they work and why you would use them. So I recommend this book to my students as well. But I'm now intrigued by this one because it's like half the price or less. And maybe it contains the same kind of information, just more concise and a little bit cheaper. So I'm interested in maybe looking at this book as well. Okay, well, like I said, I reached the end of today. Come back Thursday and we'll pick up where we left off. And also on Wednesday, I'm doing my Discrete Structures course. So if you're interested in learning more about floating point representation of numbers, then come back on 9 o'clock, not 9 o'clock, 9:30 on Wednesday, and we'll talk about that. So I hope you have a good day, and take care, and I'll see you later. Bye-bye.